In this video, we're going to talk about straight line motion, what that even means. All right, so I spent a lot of time taking derivatives of random functions, but it's important to remember what a derivative actually is. It's the slope of the tangent line. It's the instantaneous rate of change. How is my function changing right now? All right, so when we put these things together, we can actually start doing applications that use all of our derivative skills. All right, since the derivative represents the slope of a line, the units will often be one thing per another thing. Per is just the word we use for division. And keep in mind, the slope is the y values over the x values. So every unit for your outputs is going to go on top. A unit for your inputs is going to go on the bottom. So consider this function s of d, which gives the hours of sunlight d days after the summer solstice. All right, so our input is the d, which is days, and our output is the hours. So what's the units for s prime going to be? Well, s prime is a slope where our y values are on the top and our x values are on the bottom. We just said our y values are hours and our x values are day. So if I found this value, say it was like 3, that means my amount of sunlight is changing by 3 hours per day. That's a lot. Maybe it's like 0.3 hours per day or something like that. It's because as I get farther away from the solstice, I'm going to change the amount of hours of sunlight each day. And what are the units for s double prime of d? Well, s double prime is the derivative of s prime. You plug in the same d, and you get out the slope of this tangent line. All right, so our input, again, is d for day. So the output I get is the hours per day. And the input is the same thing, days. And then I can combine these, hours per day squared. So same thing I did, I'm just using my input, didn't change from the original one, but the output is an hours per day because it's the y value from the derivative. All right, one of the most common applications of calculus involves straight line motion. So a lot of times it'll talk about this like particle. So they'll put a particle on a straight line, so like dot, and it'll go right and it'll go left and it'll slow down and speed up and all this stuff. But basically, it's a straight line motion. There's one thing just moving backward and forward along a straight line. All right, so consider this. All right, you have this function p of t that gives the position in cars t miles after the start of a drive. And again, we're just going to imagine this drive is along a straight line. So you have your car. Oops, that's a terrible car. It's got wheels. And it's going kind of left and right. And the function that we have is the position t hours after we start. So our x value, our kind of input, is the amount of hours I've been driving. And the output is the miles I've gone. All right, so the units for the derivative is going to be the output on top and the input on the bottom. If I do miles per hour, this is that unit that you use when you're driving, miles per hour. What about the second derivative? We would do the output on the top, which are the values from the derivative. So they're going to be miles per hour. And our input is still hours. So this is miles per hour squared. All right, so how are these all related? Well, if I'm talking about position, the position of my car, the derivative is miles per hour. It's how fast my car is going. And then if I know how fast my car is going, the next one I get is this. All right, this one you might not know, might not be aware of, but when you have this square thing, this is the change in your speed, which is your acceleration. All right, so this is the kind of relationship between derivatives and motion, and it looks like this. All right, if I had the position of some particle, some car, or something, if I take its derivative, that's the same as its velocity, which is like speed. The only difference between velocity and speed is velocity has a sign. Velocity can be negative. So if I'm moving to the right, it's going to be positive. If I'm moving to the left, it's negative. Speed's always positive. Right? And if I take the derivative of velocity, which is also the second derivative of position, I get acceleration. All right, so which direction am I trying to go? Am I like speeding up one way or going slow another way? All right, so we're gonna use these functions in order to answer questions, and it's not normally just like, here's position, find the velocity. It'll be more kind of an applied question, like when is the object at rest? What does that mean in terms of position, velocity, and acceleration? If you're at rest, you're not moving, so your velocity is 0. All right, when is the object moving left, down, whatever? All right, if it's moving left or down, that means your velocity is negative. Like I said, velocity is different than speed because speed is just always a positive number. Velocity can be negative, and if it's negative, it means you're moving in the negative direction. So if you're moving left and right, that's left. If you're moving up and down, that's down. When is the object speeding up? The object is speeding up if I'm going a direction and my acceleration is pulling me even faster in that direction, or I can be moving to the left and my acceleration is pulling me even faster to the left. So the easy way to say this object is speeding up if v of t and a of t. All right, so if they're both positive or they're both negative, then I'm speeding up, because if I'm going in the positive direction and I'm accelerating in the positive direction, it's going to pull me further and faster that direction. If they're both negative, then I'll be going to the left, and it'll be pulling me faster to the left, and I'll be going even faster, so I'm speeding up. All right, if they are going in opposite directions, say I'm going to the right, but my acceleration is pulling me back to the left, it's going to slow me down until I eventually start going to the left. All right, so they have to be the same side to speed up, opposite sides to slow down. All right, so particle moves along the x-axis and we have its position. When is the object at rest? Well, we know it's at rest from that last slide when our velocity is equal to 0. But velocity is the derivative of position, and the derivative of position is going to be x squared minus 5x plus 4. Using the power rule, I can solve this equation now using my skills with quadratics. All right, and these should have all been t's the whole time. I don't know why I switched to x's. But I'm at rest at time equals 1 and 4. So if this was a car at 1 hour and 4 hours, my car is at rest. In the particle questions, normally it's like seconds, so after 1 second and 4 seconds, or whatever the units are, that's when my particle is at rest because my velocity is 0. Our particle moves along. When is it moving to the left? So if I'm moving to the left, if my velocity is less than 0, my velocity is the derivative of position, and the position is the derivative of this. X squared minus 5x plus 4 is less than 0. We just saw that this is x minus 4 times x minus 1. And this is something we're going to start having to do a lot, is kind of figuring out where things are positive and negative. And here's the way you do it. You figure out when it's 0. So instead of this inequality, I'm just going to consider when is it exactly equal to 0. And we already saw that's 4 and 1. And I'm going to make a number line. And so on my number line, I have 1, I have 4. All right, make sure you put them in the correct order. All right, turn to our number line. And then what we're going to do is just the basic idea is if you think about a graph, the only time your y values change from positive to negative is it has to cross the x-axis when it's 0. So when my function is equal to 0, those are kind of the border points between all of these negative values, all of these positive values, all of these negative values, all these positive values. So the zeros are kind of the borders of these things. So 1 and 4 are going to be borders. And it's going to figure out where am I in each one. So this is called using test points. I'm going to pick a test point in each of these regions. So 0 is in this region, 2 is in this region, and 6 is in this region. And for each of these regions, I want to know, is my velocity positive, like up here, or is it negative, like down there? So I'm going to plug these into my velocity, which is here. So if I plug in 0, I get 4. That's whole area is positive because 4 is positive. Everything's positive there. If I plug in 2, see 4 minus 10 plus 4 is negative 2. I get a negative number, so all those are negative. If I plug in 6, 36 minus 30 plus 4, 10, that's all positive. So when is my object moving to the left? Just in that middle section, it's moving to the left from 1 to 4. So the time of 1 second to 4 seconds, 1 hour to 4 hours, whatever it is, that's when my object's moving to the left. This process of creating this number line is something we're going to start doing a lot more often. All right, last question. At time t equals 3, is the particle speeding up or slowing down? So for speeding up or slowing down, we need to compare the velocity and the acceleration. So the first thing is, let's find both those. Velocity of this one we've already found. It's the derivative. And that is x squared minus 5x plus 4. And the acceleration is the derivative of velocity, which is the second derivative of position, which is 2x minus 5. Now the question gives us my specific time, t equals 3. If it didn't give me a specific time, I would have to do number lines and stuff, which we'll do in class. But for now, it just gives me exactly at 3. My velocity is going to be 9 minus 15 plus 4. Negative 6 plus 4 is negative 2. So I'm moving to the left, and my acceleration is 6 minus 5 equals 1. So my velocity ends up being negative 2, which means I'm moving to the left. My acceleration ends up being positive 1, which means it's pulling me to the right. And since those things are going to cancel out, I am slowing down. All right, so that's the kind of process of figuring out speeding up or slowing down. You have to compare your acceleration and velocity. If they agree, so this was also a negative 1. If they agree, I would have been speeding up, but they were different, so I'm slowing down. All right, so this was a long video, but the most important thing to remember just in general is velocity is the derivative of position, and acceleration is the derivative of velocity. So there's kind of this hierarchy that I work my way down by doing derivatives. If you're curious what happens if you take the derivative of acceleration, you get something that's called the jerk. It's like jerking you really quickly in one direction, and I have no idea what the derivative of the jerk is, right? But that's kind of the hierarchy we're working with the comparison between physics and the derivative.